Okay, welcome back. So in this lecture, we're going to look at the oral administration route for a drug, and this is section 5.3 in the type notes. So the idea here is that in oral administration, the drug has to pass through the gastrointestinal tract, the GI, before making it into the systemic circulation. So inside the GI tract, the drug concentration, or really the amount of the drug in the GI tract, is governed by first order kinetics. So the rate of change of the drug amount is minus Ka times AGI, where Ka is a rate constant. Crucially, this equation 1 here for the drug amount in the GI tract, this is not for a compartment. So the GI tract is not considered as a compartment in this type of model. So AGI then is given as S times F times D. So S is the salt factor. We had that before. F is new. It's the bioavailability. And it refers to the fact that not all of the drug that is taken orally passes the GI membrane. Only a fraction F is. So D then is the dose. So we solve this equation 1 with the given initial condition, SFD, to get that the amount of drug in the GI tract is SFD times e to the minus KAT. This will be our equation 2. The idea then is that equation 2 gets fed into a one compartment model for the systemic circulation and the tissue. And yeah, these are lumped together in the one compartment. So this new addition to the model, it manifests itself as an extra, what I call source term in the one compartment model. So before we had dAB by dt was proportional to elimination. So the drug out of the central compartment. But now we also have drug entering the central compartment from the GI tract. So in other words, it's in minus out, conservation, or absorption minus elimination. And the absorption, so that's what's coming in from the GI tract, that's going to be Ka times AGI. And the elimination is what we had before, KAB. So this is the new source term. So what leaves the GI tract over here now gets in to the systemic circulation as a source term. So I get a new equation. dAB by dt is Ka AGI minus KAB. So Ka and K are different rate constants. Or rearranging, I've got dAB by dt plus KAB, so I've taken that over to the left, is equal to Ka AGI. But I can rewrite that as Ka times AGI, which is SFD e to the minus KAT. And that will be my equation 3. Equation 3 is a standard linear ODE, inhomogeneous linear ODE, so there's a source term. And it can be solved using the integrating factor technique. So the integrating factor here is e to the KT. So I would multiply both sides of equation 3 by e to the KT. And the left-hand side, I get e to the KT, dAB by dt plus KAB, is equal to the right-hand side, KASFD times e to the k, so that's my multiplication, and then the minus KAT. Now, the whole point of integrating factor technique is I can rewrite the left-hand side as the d of something. So the left-hand side can be rewritten as d by dt of AB e to the kt. So now I have d by dt of AB e to the kt is equal to the right-hand side, Ka SFD times e to the k minus KAT. I would now integrate both sides from t equals 0 out to t. And so on the left-hand side, I'm doing an integral and a d by dt. So these are self-canceling operations. And so I'm left with AB e to the kt evaluated at the endpoint t minus the start point t equals 0. And on the right-hand side, I have a constant Ka SFD, and then I have the integral of e to the k minus KAT dt. I use the fact that AB at time 0 is 0 because the drug in the GI tract the drug is all in the GI tract up to time 0 when it enters the systemic circulation. So at this time 0, there's nothing in systemic circulation at all. So AB0 is 0. So yeah, this means the lower limit here is 0, no contribution. So I only get a contribution from the upper limit. ABT e to the KT is KA SFD, and I do my integral now. So the integral of the exponential, it's 1 over K minus KA times the exponential again, e to the K minus KAT, evaluated at the different endpoints. So the endpoints will be the exponential e to the K minus KAT minus the exponential at 0, which is just 1. And now I kind of cancel both sides by the e to the KT. So I get AB at time t is Ka over K minus Ka SFD e to the minus Ka minus e to the minus KT. This is my equation for single compartment model with oral administration. And this is equation 4. Okay, so next I'm going to go through this worked example with you. So here we're given the plasma concentration time data for a drug that's administered to a healthy volunteer. And the data are shown in this table. The initial dose is 100 milligrams, and we're asked to analyze the data and determine K and Ka. And we're given that the salt factor is 1. So we have the time in hours and the plasma concentration in milligrams per liter. And we're given the initial dose. And this is oral administration. So we have our model. It's this equation 4. The model is for AB, the amount of drug in the body. So we need to convert this to a concentration before we can fit the model to the data. Yeah, so we need first of all to convert the model for AB into a plasma concentration CP. For this purpose, we introduce what I call an effective volume, such that the amount of drug in the body divided by the effective volume is equal to the amount of drug in the plasma divided by the true volume of the plasma. So everything on the left-hand side here, let's take a look at it again. It's the amount of drug in the body, AB, divided by VD, the effective volume. And this now, by definition, is the right-hand side, which is CP. So this is what we get from the data. This is what we get from the model. And they're related by this effective volume, VD. And just the correct term for this is the volume of distribution. So referring back to the model, which is for AB, I would just divide the model by the volume of distribution, and I get CP. So CP will be Ka over Ka minus K times the dose over VD over F. So this is where the VD comes in. And then times my exponential terms. This will be my equation 5. And note here, I've taken the salt factor to be 1. So we're going to do a lot of work on equation 5. So what we have is the model, equation 5, and it has 3 parameters. And I bundle them together as if you like a vector, x. And the 3 parameters are Ka, K, and just the group VD over F. And we also have the data in the table in 5.1. So what I do here is that I fit the model to the data using nonlinear least squares, just like what I did in the lectures on epidemiology. So I introduce a cost function J, which depends on the vector of parameters x, and the parameters are Ka, K, and phi, phi being the group VD over F. And just by trial and error, I make the cost function into a least squares, but I look at the log of the model minus the log of the data. And then this epsilon here is just a little regularization. So the reason why I do the log is I've got some exponential growth going on. And it's the cost function somehow better captures this exponential growth and exponential decay if I take the logarithm. So that's what I do here. And it's a sum over the different data points, and the data points are TI, and this is time in days. So what I have to do is I have to minimize this cost function as a function of the parameters x. So I've done this in a sample MATLAB code, and it's given in the type notes in some listings. I'll just show you the sort of idea here. Well, I run this code and I get some results. In particular, I get values for K, A, K, and BD over F, my fitting parameters. And I get a very nice curve with excellent agreement between the data and the model. So another important thing that they look at in pharmacokinetics is the so-called area under the curve, the AUC. And people working in this field get very exercised by the fact that the AUC is an integral. But that's no bother to us. So the AUC, it's just the integral from 0 to infinity of Cp dt. So using the model back in equation 5, it's Ka over Ka minus K times the dose over Vd over F. And then doing the integration gives me these rate factors. So I just plug the fitting parameters that I got into my expression for the area under the curve, and I get an estimate for the area under the curve, 21.6 milligrams hours per liter. The clearance is another thing that's of interest. K times the volume of distribution. So what I can actually work out is the clearance over the bioavailability, CL over F, because that would be K times VD over F, and K is a known fitting parameter, and VD over F, this grouping, is also known. So I get that the clearance over F is 4.62 liters per hour. So this is a nice example. And when you look at, textbooks or little online intros to PK, they'll always show this kind of curve, which is you get the spike when the drug passes the GI tract, and that's a sharp spike, and then this slow decay as the elimination happens. So it's nice that after these two lectures we can understand this process, and we look at this more in detail in the following lectures.